Hello friends, welcome back to our MOOCs course on the topic of principles of mechanical measurement, and today we are into the second lecture of our first module where we are just setting up the initial concepts about the topic of measurements. I hope all of you are well, and actually I am very much interested to know your feedback about the first lecture. But despite having so many years of teaching experience, I am going to be a bit uncomfortable throughout this course simply because I don't have a direct audience in front of me, and I am not able to see into your faces, which generally always gives me an idea about whether I am going into the correct direction, whether I need to stress a bit more on a particular topic or not. And quite often the questions that keep on coming from your side during a live class or during a normal classroom hours, that allows me to go back to some concept, explain a bit more, find a few more examples maybe. Well, here I don't have a live audience. Whatever I have is only this tablet where I am doing all these stuffs, and also the camera, and all of you are on the other side of the camera. So only thing to make this course as much interactive as I can, only thing that I can do is to request you to send your immediate feedback after every lecture, and write to me whatever queries you have immediately after going through a lecture through the portal, and I will try my best to answer within the shortest possible time. And you must have seen the contact details of my TAs, also the course TAs, on the course web page. You can write to any one of them also, but all the three TAs and me personally, we shall be checking the portal regularly to get aware about your queries and try to respond to that immediately. So I request again, whatever feedback you have, whatever queries you have, please write to me, and also don't hesitate to write your view about how the lectures are going. Like we have just covered one lecture, you can easily write to me, means whether you found it interesting or whether you found it boring, or if I need to improve in certain topic or not, because then only I can change the direction of my future lectures. Now coming back to the course itself, yesterday or in the previous lecture, we primarily talked about the fundamental concepts of measurement system. Like we talked about we set up a very brief definition of measurement, then the need for having a measurement, then we talked about different levels of measurement, different kind of measurement scales, that is where we have identified the equal interval scale and the ratio scale are the most commonly used ones for mechanical measurement point of view at least. And we have also talked about different kind of standards to be used during the measurement, because measurement basically is a process of comparing your measurement quantity and the corresponding standard. So it is very important to set up or select your standard properly whenever you are going for some kind of measurement. And then we ended the lecture by talking about different types of measurement. So before I start anything, let us have a little bit of exercise. As I am not in a live class, again I would have liked to get the questions from you, but as I am not able to do, I am just guessing what queries you may have, and from there I am trying to form a few exercises. This is something that we shall be trying to do at the beginning of end of every lecture, so that we can either rehearse whatever we have done in the previous lecture or get the idea about whatever we are doing in the present lecture. So this exercise is based upon the kinds of the classifications of measurement that we have done in the previous lecture. We have seen that primarily we use two kind of classification. One is direct and indirect type, other deflection, difference and null type. So let us see a few examples and try to find out from there, see examples of few instruments and try to find out which category they primarily fall. So the first example that I have here is for a very common medical thermometer. So let us try to classify it, whether it is a direct or indirect type measurement. Of course, we can take the thermometer in contact with the body of the person where we want to make the measurement, so it is definitely something of direct type. Now can you tell me it is deflection or difference or null? Actually this particular example we took yesterday to discuss about this particular classification. So here the thermometric fluid, which is mercury in common, that is able to move through a capillary tube, and the tip of the mercury column will reach exactly the point from where you are going to get the measurement. So it is a deflection type instrument. Let us move to the Next one, a common balance, another example that we have discussed yesterday. Here again you have measurement on one side, standard on the other side, so they are very close to each other, and then it is a direct measurement, the direct comparison between the measurement and standard. But what about the second category? Here also we are having a pointer which is getting deflected, but this pointer itself is not going to show the mass of whatever you have kept here. Rather, our objective is to set the pointer or get the pointer to a 0 value to complete the measurement, and that means it is a null kind of measurement where we are putting the measurement on one side and we are adding the amount of, or we are adjusting the amount of standard on the other side to ensure that the pointer comes to that null position or 0 position. So, it is the best example of a null type measurement. Let us move to a third example. This is a common pipette which we use for taking some volume of liquid or measuring the volume of liquid. So, again it is a direct type. Actually all the examples that I have here all are direct type and also we presently have idea about very few instruments. As we go on with the course and we get idea about several modern instrumentations, then you definitely will be having some more idea about indirect measurement, or you will learn more examples of indirect measurement, but presently you are sticking only to direct ones. Like where I have picked up the examples here from whatever you already know. So, talk about the second category. Here again the volume of liquid which is there can directly be observed from the scales that is there. That means we are going to take the measurement as a deflection type instrument, or categorize this as a deflection type instrument. Next one, what is this? This is a common vernier scale or a slide caliper. So, here if we want to measure the length or corresponding any other dimension of something, then we put that within this two jaw of this caliper and get the measurement from the scale which is somewhere here. Now, what kind of instrument it is? Definitely a direct kind. And what about the second category? Either what is our objective? Finally to get a 0 value on the scale or some number directly on the scale. It is not a 0 value, so it is definitely not a null kind. Whether it is a difference kind, difference means we shall be having some reading on the scale plus a reference. The value of the reference we are going to add to the reading of the scale, and correspondingly we are going to get the reading or final value of the measurement. Here also we are not having any kind of reference, so it is again coming under the deflection type. So, let us move to the example number 5. Here this is the example of a common tire gauge, something which used to measure the pressure of vehicle tires. This, where we have a dial and there is a scale on the dial of pressure. Like in the example that I have, you can see there are two scales shown. The inner one is pound per square inch, the outer one is in bar. 1 bar typically corresponds to about 14.7 pound per square inch, or commonly we call it PSI, pound per square inch. So, 1 bar commonly corresponds to 14.7 pound per square inch, and so the inner scale where you can see the readings of 10, 20, 30 etc. corresponds to that PSI, and the outer scale that corresponds to bar. You can also see it from the here, the one written on the outside will correspond to the outer scale, the one written inside will correspond to the inner scale. Now, it is again a direct measurement because we shall be taking the gauge in contact with the or in through the location where we are going to make the measurement. But what kind of measurement it is? Here again you have an indicator that is going to move over the dial, and the final position of the dial is going to indicate the final value, is not it? So, should we call it a deflection type then? Probably not, because commonly the gauge that is going to give you is going to give you only the gauge pressure. That means, if our interest is to know the gauge pressure, then we can classify this as a deflection type instrument. But if our interest is to know the absolute pressure, then you have to the final pressure value, which is the absolute pressure that we are looking for, that will be the gauge pressure returned by this gauge plus the atmospheric pressure which you have to collect from some other source, maybe from a barometer or something. That means, here we do have a reference, and hence depending on our objective, again I repeat, if our objective is to measure only this quantity, then it is a deflection type instrument. But if our objective is to measure this absolute value, then we should classify this one as a difference type instrument, because here we have a reference and then rest part of that we are measuring with respect to or with using our dial gauge or using our instrument. So, an absolute this one can be considered as a difference type instrument. And let us move to the last example that I have, that is for an ammeter for measuring the current through some kind of conductor. So, what kind of instrument is this? Again a direct type, and we can definitely call it a deflection type instrument, because here again the indicator that we have here, this particular indicator, this indicator is going to move over the dial in this direction to reach to the final value corresponding to the measurement. So, it is again another deflection type instrument. So, this we can classify any instruments into either of these three categories, and all the 6 examples that I have here are direct type, but in near future in the course you will also be introduced to several indirect kind of measurements. Now, before I move to the next slide, I would like to point out to something else. Look at this particular one. Here your objective is to measure the mass of something, and as a standard what you are using, again the mass. So, your measurement and standard both are mass, and hence this is directly giving the value of the mass of your measurement quantity. Similarly, this one is directly giving you the length, this one is directly giving you the volume of the corresponding measurement. But now look at the thermometer. In the thermometer our objective is to measure temperature, but actually are we measuring temperature directly here? Probably not, because when we take this bulk, which is a pool of mercury in common, in contact with human body, then as the human body is at some other temperature than this bulb, there will be kind of heat transfer. Let us say that our human body is at a temperature of 38 degrees Celsius, and the thermometer initially is at 30 degrees Celsius. Now, this temperature or the body being higher, definitely it is going to lead to a heat transfer from the body to this bulk or to the mercury at the bulb, and because on receiving this heat, the temperature of mercury itself will keep on increasing till it attains a thermal equilibrium with the body itself. That means till the temperature of mercury within the capillary attains this 38 degree. So, there is about 8 degrees Celsius increase in the temperature of the mercury, and like any other material, with increase in temperature, mercury also will expand in volume, and that increase in volume will be manifested as a change in the length of the mercury column within this capillary. And actually what we are measuring is the change in the length of mercury column in this capillary tube. That means while we are trying to measure temperature, we are not getting a direct measurement of temperature, rather we are only measuring the change in the length of the mercury column. Like initially at 30 degree the mercury column may be somewhere here, and at the end of the measurement, when the mercury attains thermal equilibrium with the body, your column is maybe somewhere here. That means there is this much of increase in the length of the mercury column inside capillary, and then during the calibration process we are trying to identify the correspondence between the change in this length and the corresponding change in temperature, change in the length or volume of this mercury with the change in temperature of the mercury, and that gives us a measurement of the temperature of the human body concerned. That means while we are trying to measure temperature, we are measuring it in terms of a change in length. So, while the first three kind of instrument, let us say this one and this one, we call them a type A instrument, where we are measuring exactly what we want to measure, but this is a type B instrument where we are not measuring what we are trying to measure, rather we are measuring something else and then identifying a correspondence between our objective measurement and this modified one. The same situation is happening here in this dial gauge. Here we are trying to measure pressure, but what we are measuring is only the angular deflection this indicator is having over the dial, and then we are trying to identify the correspondence between the angular deflection, and accordingly we are drawing a pressure scale on this. So, this is also a type B instrument. What is happening in case of an ammeter? Here also, depending on, there are several kinds of ammeter, but in generally most common one, we have a permanent magnet type instrument where the current which is being supplied through a conductor leads to a deflection of the conductor in the magnetic field. That means here again, while current is the actual objective, actual measurement, we are converting that to a deflection, yes, probably an angular deflection over the dial, and measuring that angular deflection, and then we are identifying the correspondence of this angular deflection with the actual objective, which is current in this case, or pressure in this particular case. So, this is also a type B kind of instrument. That means we can clearly see there are two kinds of instrument possible. One where we directly get the measurement, whatever we are trying to measure, we get the output from the instrument in terms of that only. Like in a caliper, our objective is to measure length, and our output is also coming in terms of length. But in all these type B instruments, our output is coming not in terms of the measurement, but in terms of something else. Like in case of a thermometer, our objective is to measure temperature or change in temperature, but the output is coming in terms of change in volume, or maybe change in length of mercury column in the capillary. So, there are this type B kind of instruments probably are much more common than type A, unless in very simple situations like shown here, for measurement of length or volume or mass, we can use this type A kind of instrument, but for most of the measurements we have to go for this type B instruments. And in that context, I am going to introduce you this particular term, transducer. Transducer is a device which converts energy from energy in one form to another form. So this particular process of energy conversion is often referred as transduction. Like think about the thermometer again. Here our input to the device is some temperature change delta T. Thermometer initially was at 30 degrees Celsius, and then the mercury receives initial thermometer was at temperature 30 degree, and coming in contact with the human body, it is its temperature is increasing to 38 degrees. So, we are having an 8 degree temperature difference, which is this delta T, which is your actual input signal, but your output is coming in terms of a change in length of the mercury column in your capillary. So, there is a change in the signal. While our input is a thermal signal, thermal energy, output is coming more like output is getting manifested in terms of a volume or length. Like in the tire gauge, our input is pressure or maybe force, but output is coming in form of deflection, and that the device which does that particular thing is called a transducer. Transducer can be anything, like any measuring instrument, therefore can be categorized as a transducer. It can be any device which, depending on the output, we can call it a mechanical transducer, like the pressure gauge, where your input is force and then output is coming as a deflection, which is a mechanical kind of output. Maybe in thermometer also we can call them mechanical transducer. But this is another example where some physical quantity in a transducer getting converted to an analogous signal, but here also you are measuring temperature, but your input temperature is temperature, sorry, input signal is temperature, and output signal is some electrical quantity. Like what happens in case of a thermocouple. We shall be talking about thermocouple in the concerned module, but the gist is there. Here your input has been converted not to a mechanical output like in a common mercury thermometer, rather to an electrical quantity. So, we shall be calling this one as an electrical transducer. So, we can have a mechanical or electrical transducers. We can have other types also, but mechanical or electricals are the ones which are commonly used for mechanical measurement. A transducer can be both unidirectional or bidirectional. Unidirectional means all these examples where the input is being converted to certain other kind of signal, or actually transducer can do the other one also. It can take some signal and convert to some output. We shall be seeing that examples. So, unidirectional transducer refers to only one direction of this transformation, but there are bidirectional also, which can convert your input signal to something, some other form, and again convert that some other form back to the form of your input signal. Like an antenna, the antenna receives the electromagnetic waves and convert that to some kind of audio or video signal which reaches your device, maybe the television. But it can do the other thing also. It can take the audio visual signal from there and convert that to the magnetic electromagnetic waves, sending it back to some further destination. Some similar you can also think about our phones to be similar kind of devices. Like the electromagnetic waves comes to the receiver, where it gets converted to the sound energy, and then when we are talking, the sound energy gets converted back to electromagnetic waves, and then that goes to the destination location. So those are bidirectional kind of transducer. Now transducer again we can commonly identify of two types. One is a sensor which receives the signal from some physical system and prepares an according response, like the one example shown here. It is receiving the signal in form of a change in temperature and converting that to an electrical signal which will be used for further processing. And the other one is actuator. Actuator will take the signal from some processing unit. Sensor generally sends the output to some processing unit commonly, but the actuator will take it from some processing unit or from some control system, and then will perform some kind of mechanical work. Like in case of that tire gauge, if you think of the pressure signal which is being supplied to your device has gone through some steps of conversion by some mechanism what is there, or we may think about that ammeter, that is a much better example probably, where we are supplying current as the input. Now your transducer is converting the current to a mechanical signal which leads to the movement of this indicator over the dial, that is we shall be calling that as an actuator. Yes. So transducer primarily are of two types, sensors and actuators, but we can have other kinds of transducers also. Sensors are primarily related to the input of the measurement system, which takes which is in direct contact of your physical system, takes the input and if required converts it to some other form, whereas actuator takes the input from the control system and primarily is related to the output, where it gives you the output in the desired form. We can also have passive and active sensors. Passive sensors are those which does not require any external power input, but passive sensors require an external power input, but active sensors does not require any external power input. The input itself is converted to an electrical signal, like in this case, in case of a thermocouple, where despite thermal energy being your input, it gets converted to electrical signal, and that electricity itself will be used for further processing. So that is a kind of active sensor. Examples of passive sensors we shall be seeing shortly. Next we move to the general structure of the measurement system. So in a measurement system, all the components, whatever simple it may be, whatever complicated it may be, we can generally identify three different blocks. One detection block or input block, next is the signal conditioning block, and next is the output block. This can be thought about a general structure where our detection transducer stage or the input stage takes the input from your physical variable or physical system, and if required it can also take the signal from your standard. So this input signal and calibration signal will lead to some kind of transformed or transduced signal. This transduced signal will go to the intermediate stage or the signal conditioning or processing stage. It may require external power depending on the nature of this, whether it is active or passive kind, and then the transduced signal will get converted to some desired form of output here in this intermediate stage, and this output will be going to your output stage, whatever form you need, whether you need it on some kind of indicator like on a case of dial gauge, or whether you want to direct it to some printing device, or we want to direct it to for recording to some computer CPU kind of storage, then this output will be recorded there. And if we are talking about a feedback system like controlling the input itself, then it can also send some feedback signal back to the physical variable itself for changing the value of the physical, or I should say changing the value of the input itself, which will be done by the feedback signal if required. There are several characteristics that we want our measurement system to have, like it should be low cost, it should be easy to use, do not need any special expertise, like a thermometer generally is easy, and there is hardly any expertise required to use a thermometer or common clinical thermometer. So we prefer to measure the temperature of our body using a thermometer despite having several much more accurate instruments available. The thermometer, or I should say the instrument, should be capable of surviving in a very harsh environment, like there are several situations where we may have to make some measurement in very rough situations, like think about another temperature measuring gauge which is measuring the atmospheric temperature. Now depending on the condition, it may be exposed to very high temperatures, maybe 50 degrees Celsius, maybe very low temperature, something very close to 0, or in colder countries it may be well below 0 degrees Celsius. It may be exposed to very strong wind, dust particles, etc. So it should be able to survive that kind of environment. High accuracy is always desirable. We want the measurement to be both reliable and accurate. You probably know the difference between these two terms from our previous lecture. It should cause minimal distortion to the measurement. That is very, very important, because there are several instruments which draws the energy required for its own operation from the measurement body itself, and if the amount of energy it is drawing is very high, then it may cause a change in the measurement itself. Like, think about the we are going back to that clinical thermometer again. To cause the change in the volume, or to cause the deflection of the mercury column in the capillary, the mercury itself wants some kind of thermal energy, and that thermal energy it is being drawn from the body of the concerned human. Now, if it draws too much amount of thermal energy such that it causes a change or a reduction in the temperature of the human body itself, then definitely there is something wrong with this. It should draw that much of energy only, which will not cause any change in the measurement value, or maybe insignificant change in the measurement value. And also the range of operation should be wide, and also it should suit whatever target application that we have. Next, we talk about a few examples again. First, we have a spring balance. You know, spring balance is used to measure the weight of something. So we put the measurement somewhere here, and that causes that corresponding gravitational force causes a deflection of the spring which is inside the body, and the deflection of the spring causes a change in the position of this indicator. So from the final position of the indicator, we get the value of the weight in terms of whatever unit we desire, in terms of, like, the example here shows 1 Newton on one side, and maybe in terms of mass scale, the kg mass or kg force or gram force on the other side. Now, try to identify the 3 stages here. What is your input stage here? Your input stage is this hook here, which is sensing the gravitational attraction or gravitational pull on this, and converting that to some form of again mechanical force maybe on the spring which is inside. Your processing stage here corresponds to the spring. That spring takes the mechanical pull from this input stage and converts that to again some other kind of mechanical pull of the indicator, allowing the indicator to move. So this hook itself here is acting as the sensor which is sensing the input and converting that to some kind of signal which will be used by your processing part, which is the spring. And the spring is also acting as the processing unit plus also as the actuator, because it is the spring which will make the indicator, this indicator, move. So the indicator, the movement of the indicator is going to give you the final readout. So your indicator is the output stage which will receive the actuator signal from the spring and accordingly change its position, giving you final output. This is a very, very simple example. We can have much more complicated examples also. Just without going into the details of this is an example of flow measurement using a laser based instrument, where your flow is somewhere here. We have put some fluorescent particles in the flow. So the fluorescent particles and also receiving some kind of illumination from light, and accordingly your input signal is available in forms of light. You imagine that we have some flow of some, say, some gas like air. The air is carrying some kind of particles which can give some kind of fluorescent image, or that can glow when they are subjected to certain frequency of light. That light is the input signal. That input signal is received by the process, the input assembly here, and that input assembly converts that to several series of processing in your processor, which may be somewhere here, and then finally the processor gives you the output. Your output can come in different form, like a form of signal, like a form of a chart, and several others. So this can be a very, very complicated kind of measurement process. But in any measurement process we can always identify the 3 stages: the input or signal detection stage, the processing stage, and also the output stage. Think about the thermometer again. We are always going back to the same example. What is your input sensor? The mercury bulb is the input sensor. What is your the processing signal processing stage? Again the mercury itself. And finally your output stage is the mercury column and its positioning, the position of the tip of the mercury column on the corresponding scale. So the same component can also act as multiple stages depending on instruments, which are in simple instruments we can find some kind of situation, but in other kind of instruments complicated instruments we can clearly have 3 different stages. Now the input signal. The input signal can be classified primarily into 2 categories, or we can have primarily 2 kinds of classification. One based upon the time relationship, means how the input signal is varying with respect to time, and second is based upon the nature of the magnitude of the input signal. The based on time relationship we can have static or dynamic. Static refers to the input is not changing with time, like when we are measuring mass of something using common balance, the mass of the body is not changing, and then that is a static signal. When you are measuring the pressure of the vehicle tire using a tire gauge, the vehicle tire pressure, if that is not changing, that is a static signal. But if the dynamic signal refers to when it keeps on changing with time. That means suppose we have taken some volume of water, put that on an oven, and the oven is switched on, so that heat is being added to the volume of water. Now we take some temperature measuring instrument and dip that into that pool of water. As the water receives heat, the temperature of water pool also will keep on changing, and accordingly the input that is going to your temperature measuring instrument, that is also changing. That means it is not a static signal anymore, that is a dynamic kind of signal, that is a signal which is changing with time. Dynamic signal can be of 2 types again. One is steady state periodic signal, other is non-repetitive transient signal. Periodic means where, as the term suggests, where we have some kind of periodicity, that is a cycle of input gets repeated over a particular interval of time. The other one, when there is no such kind of repetitive nature, we have non-repetitive signal. Repetitive signals can be, we can think about cycles like the time of a day. Over a 12-hour period, the time gets repeated, time itself. We can have the high tide and low tide kind of situations where the level of water in river or ocean that keeps on changing with time. And also there are several common lab scale instruments also can lead to periodic change. And non-periodic, where we do not have something like the atmospheric temperature, generally is a non-periodic kind of input, which keeps on changing with time without any kind of repetition or periodicity. Based on assumed value, we have the very common kind of input classification, analog and digital. Analog means which keeps on changing with time continuously, and for every time instant we can have a value. Whereas digital means we are picking out the value only at certain time interval, and instead of having a continuous representation of the input, we have a discrete representation of the input. Here is an example. The one at the top shown in green is an analog input. Here for every value of time we have some value of the input signal. Like here for this time we have a value of input, for this time we have value of input, for this time also we have a value of input. So theoretically speaking, we can have infinite number of values for the input signal. It is a continuous representation. Such kind of continuous representation we can get in several very common instruments like a thermometer or like a tire gauge. As the temperature keeps on changing, it is also the mercury column or tip of the mercury column also will keep on changing its position, accordingly giving us a continuous representation like the analog one. Digital, however, is we are not going to take the temperature or the signal value at all the time, rather we are going to take it only at certain time intervals. Like here we have identified this is a time this is a time where we want to take up the value, and so we are getting this particular value. And next we have decided after a certain time interval apart, we are going to take the second reading, which is here, and there we are going to get this particular one. And this way, after a fixed or changeable time interval apart, we keep on getting the values of corresponding signal, like here, another one here, another one here. That means we do not have infinite number of values, rather we have only a finite data set to deal with. Of course, how many data that we are going to get, that will depend upon the length of this time interval. Like say we let us take an example, say we are going to record the signal of something over a period of 10 seconds. Now we can definitely capture the analog signal over a period of 10 seconds, and analog signal will be coming in form of a graph, something shown very similar to this. Theoretically, we can get infinite number of data points for any time value, we can get the corresponding signal. But if we want to digitize this, then we are not going to take the continuous signal, rather we are going to take the signal only at certain intervals, and that interval is our choice or generally based upon the instrument that is available with us. Let us say we have decided to take the interval after every 1 second. So, your interval length delta t is 1 second. That means at time 0 we get a first signal. Let us let me draw it here. Say at t equal to 0 second we take one signal here, which is this value, then at 1 second we take another one here, at 2 second we take another one here. This way keep on taking signals, and total over a period of 10 seconds starting from 0 up to 10 we are going to get just 11 set of data. Instead of having a continuous representation or an infinite number of data sets, we are going to have only 11 number of data sets. If our instrument is much more advanced, instead of taking a at 1 second effort, let us change delta t to 0.1 second. That means here our first data will be coming 1 second apart, the next data will be coming at 0.1 second, next one at 0.2 second, and we keep on continuing this way. That means over one particular second we can acquire 10 number of total data, and this way over a period of 10 second we are going to get total 10 into 10 plus 1 for this particular 0, total 101 number of data set, where it was just 11 in the previous case. So, we have much higher number of data set, and this way by reducing the time interval we can keep on increasing the total number of data points that we have. Now, that will depend upon the capability of your instrument and also how much data set that we can handle or we need to handle. More number of data set, of course, this digital one is approaching the analog one. That is, as we keep on increasing the number of data sets or you keep on decreasing the time interval, the digital signal keeps on approaching the analog signal, like shown in this particular example. Here we have this analog signal initially, then we have a digital signal. The overall interval we have divided into 1, 2, 3, 4, 5, 6, 7, 8, 9, total 9 intervals. That means instead of having a continuous representation, we are going to get only 10 number of data points, or maybe just maybe one here, then number 2, then number 3 here, number 4, number 5. This way you are going to get 10 data points, and those 10 data points will be representing your final data. That means instead of having a continuous curve like this, you are going to get only a set of data, like one here, another one here, another one here, another one here, another one here, and like this, and from there we are trying to trace the final curve. But if your delta t is too large or number of data is too small, that may lead to some trouble to you. Like say you have got one data point somewhere here, next data point here, next data point here, and the final one here, only 4 data. From there, can you retrace the original curve? That is very difficult, because you have one point here, another here, and ideally we may think about there are infinite possibilities. It can be a line like this, they can be joined by a line like this, they can be joined by a line like this, etc. And from this particular point we can never come while coming to this particular one, we can never trace the in between portion, because how can we guess that this portion will be not something like this and actual one? It is so we definitely need more number of data to represent. Like in this this particular example, while we had only 9 number of data set in the previous case, here we have much larger number of data sets, so we have more points to trace back the original curve. So larger the number of data, smaller the time interval, the digital signal keeps on approaching the analog signal, and there is much higher chance of getting a correct measurement. but still digitization has its own advantage. Like in case of digital signal, we get a sine wave or basically a time varying signal, whereas in case of in analog, in case of digital we get only square waves. Like in the previous if I go back, here we are having only square signals like this. The continuous representation we get in analog, digital only discrete data points. In analog, there is a big probability of some deterioration from noise, as we are acquiring continuously the actual signal, and all those interfering signal can also come into picture. In case of analog, as we are taking only a certain point, that is highly immune to the noise. The bandwidth requirement of course can be much more. In case of analog, we can store in OF signal, but here we shall be storing more in binary or similar kind of format, and also the power requirement is also much lesser in digital, and it is much easier to process the digital signal during the signal conditioning stage, and that is why the digital signal has its own advantages, and that is why the trend for modern instrumentation is to move towards digital. We shall be discussing more about this digital signal and analog to digital conversion in the third module of our course. Now, dynamic signal periodic can be something like this. We can have several kind of representation. Once we have some kind of repetitive structure with time, we can we shall be calling that periodic signal. We can have very much more complicated shapes also, like the one here. There is definitely repetitive nature, but the signal itself is very complicated. Or another one here, again a repetitive signal, but we have to consider a big time interval like this much to see the repetitive nature. If we are not seeing over a long interval, we shall not be able to capture this repetitive nature. Aperiodic, like the variation of temperature over a period of day or over a much longer duration, any kind of weather data, that is probably the best example of a dynamic signal which is not periodic in nature at all. And in several measurement situations, we face with aperiodic dynamic signals. Now we come to the stage of calibration. Any instrument has to be calibrated to start with, and calibration means the instrument will be subjected to a known magnitude at the input stage, and the output stage, whatever response we are getting in whatever may be the form, we are going to record that and then try to identify the correspondence with your input. Like shown here, we have an instrument which is generally known as resistance temperature detector. We shall be talking the principle of this later on, but here the idea is corresponding to each temperature we measure the resistance of a conductor. So, you can see here we have a calibration table. This kind of chart is called calibration chart. Here corresponding to each temperature we have measured the resistance of a conductor and also corresponding gradient on the curve. And now if we want to measure some unknown temperature, then we take the probe or take the measuring instrument in contact with that body and measure corresponding resistance, which is coming to be this. Then we try to identify where it falls in the table. In this particular case, it is falling in between these two values. Then we perform some kind of interpolation, that is subtract the lower value from the measurand and then divide that by the corresponding slope, which is 0.3541 in this example, and that is going to give you, with the final addition is going to give you the final temperature of the unknown quantity. So, during any calibration process we have to find a calibration chart to identify the correspondence with this. Even more popular approach is to get a calibration curve like this, where your input, like here the input in this example is flow rate, but output is coming in terms of frequency of some instrument. So, these are the points where we have taken the reading, some known flow rate, corresponding frequency we have measured, and we have tried to represent them with a straight line or some other suitable curve. Then when we measure some unknown quantity, unknown flow rate, say the corresponding frequency is falling here, then easily from the curve we can identify the flow rate this. So, this calibration curve generation is a must for any instrument to start with. Generally the instruments, whenever we purchase a new instrument, simple or complicated whatever may be, that comes with a calibration chart provided by the manufacturer, but it may be required to recalibrate the instrument repeatedly after a few periods of operation. Now, when we do this calibration based upon time invariant input and output signal, we call that static calibration, and corresponding curve like this particular curve is called a static characteristic curve or static characteristic. However, when both inputs and outputs or at least one of them are varying with time, we call that a dynamic calibration, which is much more complicated, and because at every time we can have a different nature of the signal, and corresponding characteristic curve or calibration curve is called dynamic characteristic. Let us discuss about a few properties of the static characteristics which an instrument must have. The first one and the most important one probably is sensitivity. Sensitivity refers to the magnitude of change in the transducer output per unit change in the measurand. Means it gives you the slope of the calibration curve. If this is your calibration curve, say x is your input, y is the output that you are getting from your transducer, and this is the calibration curve that you have got, then this is going to give you the slope of this curve, like this much of change in your input dx, whatever change in your output that you are going to get dy, that is the sensitivity of the instrument, just like this. So, this in this particular case the slope does not change with the change in the input, so we call it a static constant sensitivity. However, we may also face situation where the sensitivity of the instrument keeps on changing with the input, then it is a variable sensitivity because it is dependent on the input. Now, can you tell me what we want? We want higher sensitivity for the instrument or lower sensitivity? Definitely we always want our system to be more sensitive. Like think about the thermometer example again. We have got a change of 10 degree Celsius temperature. Now, if the 10 degree Celsius change in temperature causes an increase of 5 mm length of this mercury column, that is in case 1, and in another case it causes a 10 mm length change of the mercury column, then which one is more sensitive? Definitely this one, because here the change in output for the same amount of input is more, so it is a more sensitive instrument. And see the use of use. Now, here over a distance of 5 mm we have to plot a we have to draw a temperature scale showing 10 divisions at least to show that, to indicate 10 degree change in temperature. That means for every millimeter we have 2 degree change, but here for every millimeter we have 10 degree change, and so much more easy to draw the temperature scale, and so we should always go for an instrument with higher sensitivity. But sensitivity does not need to be confused with accuracy, which we shall be discussing later on. Next is zero bias. It refers to the magnitude of the transducer output when you have not given any input at all. There may be several situations, like ideally in case of ratio measurement particularly, we want the output to be 0 when there is no input, but sometimes your instrument itself may have some error inside and it starts the reading from this particular point itself. You must have seen such situations with these weighing scales. You have not put anything, but it is showing some reading here. That this is what we refer to as zero error or zero bias. It can be both on positive side or negative side, like in this case. So, we have to be careful of your instruments about the zero bias, and you have to ensure that the instrument indicate zero output when there is no input, and if at all there is any zero bias which we have to deal with, we need to keep a note of that, because whatever final reading that you are going to get, you have to add that zero bias to get the actual value of the measurand. Sometimes we can have an error in the scale itself, like it is an example of vernier. You can see that the 0 has been shifted here, leading to this much of 0 error, whereas in this case the 0 of the vernier has been shifted on the other side, leading to this much of error. But truly speaking, both the 0 of the vernier scale and actual scale should be collinear, which is not happening here. It is a permanent error in the instrument, and we have to be very careful about such kind of zero bias or zero error. Next is resolution, very important for an instrument. It refers to the smallest input required to cause a change in the transducer output. Smallest change in input required to cause a change in the transducer output. This is different from sensitivity. Here, like we are causing, as initially your system is having a pressure value of this and corresponding output is this. Now, we are increasing the pressure, but the system is not able to show any output till we reach this particular level. That means, over this entire duration or over this entire range of change in input, your system is showing the same output value. Only when you reach at this particular point, there is a change in the output to this. This is called the resolution of the input, resolution of the instrument, which also gives us an idea about what is the minimum value that we can measure by our instrument. Resolution of an instrument can depend upon the construction of the transducer, can also depend on the noise of the system if anything is present there, or numerical resolution of the data logger. Here we have a situation where there are several cases shown, like this is the continuous line is the perfect representation or perfect output from the sensor which we want. See from this particular case number 1, here your system is having very high resolution, because with very small change in input it is showing a change in the output, but actually the value that we are getting, that is not matching with the actual curve. So, it is high resolution but low accuracy. If we move to this, here it is low accuracy because it is moving away from the actual curve, and also low resolution because this much of change in input is required to cause any single change in output. It is a low resolution instrument. Now, this one here we are still at low resolution because large change in input is required to cause any change in the output, but it is much closer to the actual curve. So, it is a high accuracy and low resolution. And this number 4 is the one that is the ideal situation. It is low resolution and high accuracy as well. So, this kind of instruments are always preferred. The resolution of the instrument, it is not that we always have to go for instruments with having very low resolution. Sometimes also we use another term called least count. Least count refers to the smallest value the instrument can give. It is not that we always have to measure instruments with very high resolutions. Like think about measuring time. When we are measuring time, say we are presently at Guwahati and we want to take a flight to Delhi, and we want to measure how much time is required during the flight. Now, the time is coming in the range of something like 2.5 hours to 3 hours. We can easily measure that to a common wristwatch or similar kind of watch, where and in the wristwatch, what is the smallest time interval you can measure? Maybe a minute, maybe a second. So, the smallest value that you can measure is 1 second. If there is any change in time you want to measure which is less than 1 second, your wristwatch will not give that. But the example that I am talking about here, you do not need at all. You actually do not need any second also. Minute and hour are sufficient. But you think about something, say, okay, how much time Usain Bolt takes to finish his 100-meter runs? I think the world record is 9.58 seconds. So, we are talking about measuring a time of 9.58 seconds. Then can a wristwatch give that? Definitely can't, because here we are not only trying to measure second, rather we are trying to measure 1/100th of a second. That means you need an instrument which is going to measure at least 0.01 second. That is the smallest possible value it should be measured with small change, and preferably up to a third decimal, because there are several situations where you may have to go for a photo finish, and there even 2 decimal points may not be sufficient. We may have to measure even the third decimal point also. So, there we need an instrument with such kind of resolution, but not always. That depends upon application, and accordingly you have to choose the resolution of the instruments. So, resolution and sensitivity probably are the 2 most important static characteristic a system should have. Range and span refers to the range, as the term suggests, what is the range maximum and minimum the instrument can measure to. Like the example of the run that I talked about. Here, like if in a wristwatch we can measure up to 1 hour in a dial, whereas when we are trying to measure an instrument, or sorry, we are trying to measure time with a resolution of 0.01 second, we hardly need to go for such long duration. Your instrument may give just a reading of total 0 to 10 seconds, 0 to 15 seconds, that will be sufficient for that measurement. So, range will depend on the kind of application. Like here we have an example of a few pressure gauges. You can see there are 3 pressure gauges, all are giving reading in PSI. Like in this case we are getting reading up to 100 PSI, here we are getting up to 200 PSI, whereas here we are getting up to 5000 PSI. So, there may be different situations, accordingly we shall be choosing the gauge. Another example, what is this? I am sure you know this. This is the sphygmomanometer. Sphygmomanometer, which medical practitioners use for measuring the blood pressure. Now, what is the highest value that we have here? 280. But 280, what is the reading, or sorry, what is the unit of this? We have to be careful. It is PSI, it is bar, none of them. It is millimeter of mercury. Now, 1 millimeter of mercury corresponds to very small psi, or practically 1 psi corresponds to something like 51.7 millimeter of mercury. That means this scale of 280 psi is actually going to give you only approximately 5.5 psi. That is a much smaller range compared to any one of the three, but we do not need to go for a much larger range when we are measuring the blood pressure. So, this manometer itself is sufficient in this case, sphygmomanometer I should say. Another characteristic is linearity. We generally prefer to have a linear nature of the calibration curve, but practically there are several situations we may not get, like the input output relationship may be like a curve like shown here. We are not getting a straight line here. If we get a straight line, it will be much easier to measure an unknown quantity. So, we try to get the best approximate straight line from there. There are two ways we can do it. One is to put two parallel straight lines, like let me say an example. Let us say this is your input x, this is your output y, and these are a few data points that we have got from during the calibration. Now, one option is we can put two straight lines which encompass at least most of the data and try to get a measure from there. Other is we try to find a calibration straight line, something like this, using a relation y equal to mx plus c, and from use this one, identifying the value of m and c from this calibration curve used for unknown measurement. Linearity is a desirable property, not always possible to get, but we would like to get the response as a linear one. Like here we have a non-linear response that we are getting. By digitizing this, what we are doing, we are picking up 10 points from this, and then we can see for such kind of regularized response we are getting a much linear nature. But when your response is very non-linear kind of nature, or it is a highly time variant nature, then a 10-point scale is of no use. The final characteristic that we would like to talk about, drift refers to the change in the calibration curve over a period of time. Now, once you have calibrated the instrument, because of different kinds of aging problem, wear and tear, certain damage, the calibration may get shifted. We generally have two kinds of drift, one is zero drift, another is sensitivity drift. Zero drift talks about the change in zero bias, like this dotted one is the original curve, but with time the zero, there is a zero bias that may get developed, that is zero drift. And the second one, where the slope of the curve itself is changing, that is the sensitivity drift, that in this case it is a combined curve where both zero and sensitivity drifts are present. When that kind of situation is there, we may have to go for a recalibration, like in this case this one was the original curve. Now we have we can see there is a zero drift that has got developed, and also there is a sensitivity drift, and so if you recalibrate, this one may emerge as the new calibration curve. That this drift therefore essentializes repeated or periodic calibration of your instrument. Hysteresis in certain instruments may shows a hysteresis behavior, that is the output may depend on the change in input. Like when you are moving in the forward direction for this particular input, you are getting this output, but when you are coming back for the same input, you may get this as output. And if there is a negative kind of slope while coming back again, this is the third input that we are getting. Certain instruments may show a hysteresis depending on the friction, depending on some elastic deformation that may appear, wear and tear, aging problems. Again, repeated calibration can lead to some kind of solution to the hysteresis problem. A few lesser used properties, dead time refers to the minimum time required by a transducer to initiate any response. Like in this example itself, as we are changing the input over this period, we are not getting any kind of output. Only after reaching here, we are getting any response from the output device. Now, that is called dead zone or dead space. And after showing an output corresponding to input, when we change the input signal, the transducer may take a certain amount of time, maybe in seconds, maybe in nanoseconds, but a certain amount of time to represent that on the output side. That is referred to as this dead time. Threshold is the same as the dead zone. The first value of the input for which we get the output is the threshold. Repeatability is, we have already talked about this in the previous lecture, we need to repeat the experiment using the same instrument, and if all are coming very close to each other, we consider the instrument to be a reliable one and say that it has a good repeatability. And reproducibility, truly it is not a nature characteristic of the transducer, it is more a characteristic of the phenomenon. Suppose I have done one experiment in my laboratory using a certain set of instruments and observed something. Someone else far away from there does the same experiment using different kind of instruments and observe the same phenomenon. That is called reproducibility. It is an important concept of any research, any R&D, that is the phenomenon or observations has to be reproducible, and but it is truly not a characteristic of the transducer itself. So, this takes us to the end of different characteristics that we have. We need to know static characteristics actually about an instruments. If I summarize the observations or the discussions of the day, we have talked about the transducers, actuators and sensors. Then a general measurement system, we have seen that there are 3 stages: an input stage, a signal conditioning stage and an output stage. Then we have talked about different types of input signal: digital and analog, time invariant and time variant. And then we have talked about the process of calibration, corresponding static characteristics and dynamic characteristics. And finally, we have talked about different kind of static characteristic a system or a transducer should have. The most important characteristic for a transducer is sensitivity and resolution. It should have high sensitivity, it should have a linear kind of nature. Resolution will depend on the application. The drift should be as low as possible, and the hysteresis kind of error, if those are ideally, that should not be present in the instrument. So, we shall be continuing with this module 1, where we shall be discussing about the different kinds of errors that may creep in your calculation and how to eradicate those errors, and a few other relevant discussions to close up this first module. So, please wait till the next lecture. Thanks for your attention for the day. Thank you.